Gary, you're still.
Guys, what are you going to do? You know?
Good morning.
Good morning. Welcome to the first day of the 2024 American Gem Trade Association Tucson Elevated Seminar Series, sponsored by the American Gem Society. Our third session this morning, before lunch, good for you. A canary in the ruby mine, low temperature heat treatment, experiments on Burmese ruby. One of the challenges that we face in the industry is trying to determine the treatment of gemstones, and low temperature heat treatment of ruby is extremely difficult and challenging for those of us who are desk gemologists. Fortunately for us this morning, we have two excellent gemologists to explain what is going on and how they do the identification technique. On the far left, we have Billie Hughes. Billie is an award-winning photographer and photomicrographer, as well as laboratory gemologist. She's outstanding. And Wim Vertriest is GIA's field gemologist?
That's correct.
Sounds good. Field gemologist. He goes out into the field. They find stones. They bring them back for research, and they keep them there in the Bangkok GIA lab for identification purposes and for research. And with that, I will turn the podium over to Billie Hughes and Wim Vertriest. Please welcome.
Thanks, Gary.
Thank you, Gary. Well, thank you all for coming out today. Wim and I are really excited to be here in Tucson with you. And as we get started on this conversation about low temperature heat treatment experiments, I wanted to start off by providing a little bit of background as to why we wanted to do these experiments. Now, heat treatment is not actually a very new treatment to stones at all. It's been going on for over 1,000 years, and for much of that time, heat treatment in ruby and sapphire looked something like this. This gentleman is doing treatment in Sri Lanka using a charcoal stove, and these would be relatively low temperatures compared to what we can reach nowadays. And so I think that's one of the misconceptions, is that there's a lot of talk nowadays about low temperature heat treatment, but it's not actually something new. It's actually the more traditional type of heat treatment. But over time, as technology improved, treaters were able to push temperatures higher, and so nowadays a lot of the treatment looks more like this. This is our friend John Emmett, and with modern technology, we've been able to bring the temperatures higher and higher. And now treaters can dial in a lot more specific. So they can choose a specific temperature, they can choose the exact amount of time that the stones are at that temperature, and do things like modify the ramp rate. And so with this change in technology, what we have found is the market has changed with it.
all data on all stones 6 different times. So imagine the pain that Billie had to go through to take the exact same inclusion photo in this exact same orientation 6 times on a ruby that sometimes changed a little bit, sometimes changed a lot. So that's a lot of effort that goes into it. And I think here we see this image where we see a lot of the stones that we looked at the different temperatures. And you can already see some of the impact of the treatment. And I think the most noticeable impact is that some stones get destroyed. You see, like, I think stone number 30, at 900 degrees, it breaks in 2 pieces. And actually at 1100, we kind of lost that piece because it shattered even further. So the impact of treatment of these stones is not always positive. Not every stone you put in the furnace comes out better. And I think we have one great example here where we see a stone, and obviously if we try to improve this stone, I think we would all agree it's the left-hand side of the stone that needs a little bit of improvement there. Because the right-hand side, okay, we see this crystal with like a little bit of a yellowish cast, but it's not super obvious. It's that big dark patch on the left with that fracture. That's something that we'd like to improve. So once we heat treat this, we actually see that that left part, it did improve. That fracture became less visible, that patch still became less visible. But the part that didn't need improvement actually became a lot worse. Because there's a huge fracture that developed there, that lightly yellowish crystal, transparent, became almost opaque and like a murky gray. So this is something that we have to keep in mind, that even when you heat treat stones, you can't predict the outcome. There's a lot of things that can go wrong. It's not always just improving the stone. So even if you take a stone, you put it in the furnace, you're always risking it a little bit. So that's what happened during our process as well, where several of the stones actually were destroyed during the process because we took it too far, or just because the stone wasn't suitable for heat treatment. Now another challenge that we had was communicating between us, because while in the US nobody could leave their home, it was more or less the same in Bangkok as well. So we had to send stones between 2 different laboratories, because we're both based in Bangkok, but Billie works at Lotus, I work at GIA. So we had to send these stones around, but we couldn't see each other in person. So we had to find a way to communicate about each other, about these stones, because we're looking at inclusions, which means that we have to know exactly which inclusion we're talking about. And a lot of these inclusion scenes are quite hectic, quite chaotic. If you've ever looked in a Burmese ruby, there's a lot going on there. So to make sure that we were talking about the same thing, we draw these maps. Well, I asked the 4-year-olds to draw these maps, so we could really communicate about which inclusions we were talking about. And I think on the bottom row here, those 4 crystals, I think you can see they're going to come back later. You're going to recognize that in an image. So here's that image that that 4-year-old drew, and this is how that translates. This is basically all the inclusions that we thought, okay, this could be of interest, and this is my 4-year-old's work, and this is what Billie made of it. So you can see, like, it allows us to communicate about which inclusions we're talking about, because at this point we didn't even know which one is calcite. So we cannot talk about the calcite inclusion in this ruby, because even if we analyze it, there's usually like 12 calcites in there. So which one are we talking about? Because it is very important for us to know which inclusion exactly we're looking at, because we have to compare the same inclusions to each other. We can't compare apples and pears here. We have to compare apples to apples, especially when we take it through all these heat treatment steps, especially with all the data that we collected there. So Billie's going to explain now like, what actually happened to these inclusions.
Yeah, so one of the focuses of our study was the inclusions and how they would change at different temperatures. And of course, what we were really hoping for was that a lot of them would change at the lower temperatures that would help us detect this treatment. So let's take this for example. This was a crystal in one of our unheated samples. We did analyze it and find out that it was calcite, the one that we saw the most commonly. And after heating it, we found that even after the first round of heating at 600 degrees, there was already a change in the appearance. This big shiny fissure appeared around the crystal. But we did several more rounds of heating. So we heated it again, and this is what it looked like after the next round at 750 degrees. And so you'll notice that this fissure is actually starting to heal at the edges and develop these elongated channels. After 900 degrees, it looked even more different, and those channels started to become more complex. And what we're really starting to see here is the formation of what we call a fingerprint, or a partially healed fissure around the crystal. At 1100, it was changing even more, and you start to notice a little bit difference to the texture of the crystal as well. It's becoming a little bit more opaque. And I shot that in dark field as well, just so you guys could see that change and how frosty the crystal starts to look. And I want to say I tried to keep the lighting as consistent as possible from one step to another, just so we could be comparing apples to apples as much as we could. But there may be a few cases like this where I adjusted the lighting just so you could see it a little bit more clearly.
That's one thing I do want to stress with all of this. This is all considered low temperature heat treatments. So all of this is below that boundary of 1200 degrees, so yeah.
Yeah, exactly. And so we were pretty pleased to see this, actually, because it does show us that we can start to see changes in some of these solid crystals before the rutile might start to dissolve. Here's another example. This is what the crystal looked like unheated. And this was a mica crystal. Again, one of the most common crystal types that we saw in this material. One of the reasons I like mica is it's not just present in a lot of Burmese rubies. We see it a lot in Mozambique rubies as well, which is very important in the market. And so this is something that has implications not just for testing Burmese rubies, but for rubies from other origins as well. So we wanted to see how this mica would change. And at 600 degrees, we didn't see too many changes, although you can start to see at the top that some of the other crystals started to alter and develop a little fissure. And so that was part of what we noticed in this experiment. Not every crystal started to change at 600 degrees, but we heated it again, and by 900 degrees, we did see a significant fissure start to develop around this mica crystal. And we kept heating, and you'll notice also that in the background you start to see some kind of glassy discoid features appearing as well. And keep an eye on that fissure, because at 1100 degrees, we start to see it form into a fingerprint, and we start to see these channels develop. And this was a lot of fun for us, because working in the lab, we really see fingerprints in stones every single day. But it's not every day that you get to watch a fingerprint form. And so this was really interesting. By 1500 degrees, which was our higher temperature round, which we did for contrast, you could see that the stone had started to change dramatically. There's an immobile bubble that has developed in the mica crystal, and even that fingerprint has become very bubbly and almost unrecognizable. Here's another example of a crystal in an untreated stone. This was again one of the more common minerals that we saw. It was a spinel. And this spinel was pretty tough. It actually didn't start to alter until we got to 1100 degrees. And so again, we're noticing that not all the crystals change at the same temperature, but we're still below the high temperature heat treatment threshold. And we did heat it higher at 1500, and again, you notice that the texture has become very frosty, and then it looks almost opaque now. You really can't see through it anymore. Here's another scene that I found really interesting. This is unheated as well. What I like here is that you have 4 different crystals to look at. 3 of them are mica, one of them was garnet. And so as we were doing this, we were thinking, do you think all the mica is going to change at one stage? Will the garnet change at a different stage maybe? That was kind of my prediction, was that them being different mineral types, they might react differently. So we heated it at 750, and that's when we started seeing the changes. And what I found here was kind of interesting is because the 2 mica crystals that are on the left started to develop fissures, and the garnet at the top right also got a fissure around it, but the 3rd mica crystal doesn't really alter much. And that was a little unexpected. I thought the micas might all change at the same temperature, but they really didn't. And what might account for this? Well, there are several factors going on when you're heating a stone like this. It's not only about what type of solid inclusion you have. There's a lot more that could be going on. Things that could be influencing how these crystals react to heat include where they are in the stone. Are they close to the surface, or are they deep inside the stone? How big are the crystals? Maybe smaller crystals may not have as much strain around them. Things like the orientation of the crystals might make a difference. And we also have to remember that some of these inclusions have inclusions of their own. So there might be something else inside of those crystals. And I also want you to notice that, we're talking 750 degrees. You notice all that rutial silk, all those needles in the background? Notice how they aren't affected by the heat at all. They still look like they're in great shape. And they're still intact at 900 degrees as well, but at this point, all 4 of these crystals have started to show signs of heat. So we've got fissures around the mica, all of the mica at this point, and the garnet. But also you'll notice that the texture of these crystals is starting to change and get a little bit frostier. But again, that rutial silk looks completely undamaged. And this is one of the takeaways, really, is just because we see rutial silk that's undamaged doesn't mean we're looking at an untreated stone. By 1100 degrees, the crystals have changed quite dramatically, and the rutial silk is still very much intact. And it's really only at 1500 that we see that change. And now all of a sudden that rutial silk has begun to dissolve. And you can still see traces of it in small particles, but you really don't see those nice long needles anymore. And the crystals, of course, have changed dramatically. Many of them have developed bubbles, immobile bubbles inside. Now, not every crystal was as sensitive as the mica, the spinel, the calcite that we've been looking at. Not all of the crystals changed at these lower temperatures. Here we have that sphene crystal, which was that kind of yellowish crystal we were looking at earlier in sample 10 in the corner. And this one was actually very resilient to heat. And we heated several rounds without seeing any changes to the crystal until we got to 1100 degrees. And you can see even then the changes are fairly minor. You have some small fissures developing around the edges. Maybe they're healing just a little bit, but we're not seeing dramatic changes here. And we really didn't see those dramatic changes. Here it is in dark field, just so you can get a better sense of the texture. And again, this is the importance of lighting. So it's a little harder to see some of those texture changes here in transmitted light. A little bit easier to see it in dark field. But again, we're still not looking at really dramatic changes in this crystal until we get to 1500 degrees. And that's where we really start to see the changes in texture, the big fingerprints forming, that kind of drippy, melty appearance. And so it's important to notice that some of the crystals might not be as sensitive. Here's another example of that. We have a little rounded apatite crystal, and this is what it looked like unheated. And we heated it round after round after round, and we really didn't see any changes in it at all. You can see that there's also a bunch of rutial silk in kind of clouds, angular clouds around the crystal. And it was only at 1500 that we saw significant changes. And again, the apatite starts to alter, but so does the silk, which has become a lot of dotted particles. And so it can be helpful for us to know what kind of crystals we're looking for. Because, for example, you might be testing a ruby in the lab, and you might notice that there's 2 different crystals, and one of them kind of looks heated and melted, and one of them hasn't. And you might be inclined to say, this one crystal looks like it's perfectly intact, so maybe the stone's not heated. But again, it can help to do a Raman and figure out what we're really looking at. And if you've enjoyed looking at these inclusions today, I would also encourage you to visit the Hyperion section of our website, which is on lotusgemology.com. And we've put together an inclusions gallery in a searchable database of all different kinds of inclusions. We've got ruby, sapphire, things like emeralds and spinels as well, natural and synthetic stones. We have treatments listed, origins listed, and you can really compare and contrast a bunch of different inclusion photos. It's something we add to regularly, and currently we're already at over 1,600 images in this database, and it's available for free on our website. And so I encourage you afterwards, if you're interested in this, to visit. And if you want, you can just take a photo of this QR code so that it's really easy to look that up later. So I'll give you guys a second to take a picture. So let's get into another section of the experiment.
Yeah, so I'm going to take over again and go a little deeper on the R word that Billie has occasionally dropped already, Raman, because it's a word that we've been hearing a lot in gemology and is very important for modern gemology. But I see there's a couple of very advanced professors in gemology here, but most of us aren't really familiar with this technique when we start our gemological journey. So I wanted to go a little bit more deeper into what the impact, what the potential, what the limitations of Raman spectroscopy are, especially applied to our project. So we're not going to travel back to central Italy 2,000 years, that's the Romans. We're also not going to have lunch with some hearty Japanese soup, that's ramen. We're going to talk about this gentleman, Sir C.V. Raman, who in 1928 discovered a spectroscopic technique to determine vibrational modes of molecules. I think that's 100% clear for everyone, right? So this man is a very important scientist. He was the first Asian to win a Nobel Prize in any of the sciences. The day that he published his result is still seen as the National Science Day in India. So a very important discovery that impacted a lot of science worldwide, but has really only made its way into gemology in the 90s and is now becoming very accessible to all gemologists. So that spectroscopic technique to determine vibrational modes of molecules. We're going to break that down in little parts so we all understand what that means and how we can apply that to gemstones. So I think everyone's familiar from their basic chemistry classes that everything we see around us is built out of molecules. And we've all seen these models with little balls connected with sticks. And we think that is what most matter is built of. But in reality, what's happening is that these things look like this. They wiggle and jiggle in any direction possible, and instead, those are the vibrational modes that we're talking about. Let's take a look at it again, because it's so cool to look at. So this is a very simple molecule, but imagine this happens in very complex molecules as well. So this is what we mean with vibrational molecules. It is not those static wooden-colored balls that we remember from our chemistry class. These things are always wiggling and jiggling. So what we mean with the spectroscopic technique is basically we shine light on it and we see how that light interacts with the material. So what happens in Raman spectroscopy is that we send a single wavelength at it with a laser light, and that reacts with those molecules. So those molecules are bouncing around, wiggling and jiggling, and some of the light just comes back as it is. But because it interacts with that wiggling and jiggling and that vibration of these molecules, some of it gets shifted around a little bit. So it gets shifted to a different wavelength. So that's what we see. We see a lot of the light just comes back, and some of it gets changed a little bit. And when that's changed, it shifts to a different wavelength, and that is determined on which vibration, how much the wiggling and jiggling is happening in that molecule. So this is what a Raman spectra looks like. We've got at zero, we've got the light that we send into it, and then on the right we see some light that shifted 218, some 314, some 459. So that is determined by which molecules are present and how strong they are vibrating. So here are some examples that we're all going to be familiar with if we look at Raman spectroscopy. We're going to start with one of the simplest and at the same time most complex materials in the world. But the diamond is actually a fairly simple structure. We've got one building block, carbon, and there's only one change in direction, there's only one way that it connects to each other. So we actually only have one vibrational mode there. Which means that one building block, one vibration thing is going to result in one single Raman peak, because we've only got one direction that it's going to change. So this is what a Raman spectra for a diamond looks like. So this is one single peak. Now obviously not all gem minerals are created equal, and a lot of gem minerals are way more complex than this. We're going to jump straight into the big one, tourmaline. I've written the chemical formula down. We basically have the option to play around with around 21 different building blocks. So that already offers so many possibilities. These 21 different building blocks offer us options to connect them all in different ways. So we can expect that a Raman spectra is going to be a lot more complicated, because there's a lot more options for different dancing partners for that vibration, also different intensities that are going on there. So this is what the Raman spectra of a tourmaline looks like. So these Raman spectra are really determined by which ingredients are in your mineral, which are your building blocks, and how they interact with each other. And that means that for every single mineral, we're going to have a Raman signature. So it's going to relate to that structure and the composition of it. So Raman spectroscopy can give us a lot of information about the material that we're looking at. So it's very helpful for identification. In the hallway there are a few manufacturers of Raman units for identification of gem materials. That is super easy, super fast, super straightforward. But also that unique crystal structure, there could be some variation there. The structure of the same mineral isn't always exactly identical. Like we see, if we ask you all to draw, to make a drawing of a car, it's all going to be a car, obviously, but every car is going to be different. So the same is happening with minerals. Because minerals, they can be a little bit damaged, they can be a little bit crooked. And that could be reflected in that Raman spectroscopy. And that is of very high interest for us. Because I think one of the examples that we are most familiar with is zircon. Because zircon can be metamict. It means that it's basically been damaged by its own radioactivity. So we've got a non-metamic spectrum on the top and a metamic spectrum on the bottom. And we see that those peaks are not as sharply defined. So the sharpness of that peak is very important as well. You see that some of these peak positions have shifted a little bit. So that's something that we know from gemology pretty well, that the properties of a metamic zircon could be a little bit different from a non-metamic zircon. So that's the same thing in Raman spectroscopy. So we wanted to apply that whole concept to our heat treatment project, because heating can damage a crystal structure. So we wanted to see if we can pick that up with Raman spectroscopy, and if we could correlate that with visual observations, or maybe see more than we could detect visually. So that's what we were after, collected a lot of Raman spectra on a lot of different crystals. Again, this is my amazing drawing, from that 4-year-old. And we're going to look at those 4 crystals at the bottom, which are all calcite crystals, which I think also is very important to remember the point that Billie made. It's not because these are the same types of crystals that they're all going to react the same. And I think this is going to highlight this very well. So here's that series of these 4 crystals, and we're going to start with looking at the one on the far left. So we're not going to focus on the other 3 for now, but you see in an unheated state, it looks kind of cute. But at 600 degrees, we don't see a lot of change there. 750, we don't see a lot of change either. We take it to 900, kind of looks the same as before. So if we look at this left crystal, even up to 900 Celsius, it didn't really alter that much. So are we seeing the same thing in that Raman spectra? So here we have the Raman spectra on the same crystal, where especially for calcites, we focus very heavily on that peak around 1100. And we see that that peak remains super consistent. It doesn't change position. There are no other peaks that start showing up. So we see that that crystal remains very undamaged, even up to 1100 Celsius. So this perfectly confirms what we saw visually, because visually we didn't see any changes in the stone, but the Raman spectra are confirming that. Now let's take a look at the same picture, but focus on the third one from the left. Again, we are looking at a calcite crystal, and in an unheated state, up to 600 kind of looks okay. There's this fracture coming in, but that's coming from a different crystal below it, which is in the original photograph. But once we hit 750, we see that the bottom of that crystal is starting to get very frosty. It is not as transparent anymore, it's becoming that cloudy white. And once we're up to 900 Celsius, we see that that entire crystal is frosty white. It lost all its transparency, so it's kind of opaque right now. So we want to see, do we see the same thing in the Raman spectra? Here again, we've got the comparison where we see the change from 600 to 750, that frostiness really comes in. So here are the Raman spectra, where from the bottom we start at unheated 600, 750, 900, 1100. And here we see a very dramatic change. So once we cross that 750 boundary, we see that the carbonate peak at 1100 almost completely collapses. That peak becomes very short, it becomes very wide, almost drowns in the noise. And we see these other peaks showing up around 350. So what we're seeing here is the breakdown of calcite, calcium carbonate, into calcium oxide and CO2. So the peaks that are appearing here around 350, those are the calcium oxide peaks. So we're seeing a new mineral appear, and that is that frostiness that we see in that crystal, where that calcite is literally breaking down into 2 components, and they look very different from the original calcite. So again, very nice observation where we can see one-on-one that relation between the visual observation and the more advanced Raman spectroscopy. Now, Raman spectroscopy in gemology, one of the most commonly used applications is to detect heat treatment in spinel. Now, spinel is being heat treated occasionally, and the Raman signal of spinel changes a little bit. So we use Raman spectroscopy and the related photoluminescence spectroscopy to detect this technique. So we wanted to see, can we use the same criteria that we use for gem spinel in the inclusions as well? Because the spinel inclusions are very common in Burmese rubies. So here we're looking at a spinel crystal. So the one on the top, it's got another crystal in front of it, so it's not a bubble, it looks kind of like it, but we're looking at that crystal behind that crystal with very high contrast. You see there's a lot of things going on here, so we're going to see a lot of changes, but focus on that spinel crystal with the arrow. Because that spinel crystal isn't really changing, but the other crystals are changing very dramatically. But the spinel, it doesn't care. 750, it's okay. 900, it's completely okay. And even if we take it a bit higher than that, it was completely unaltered. All the other crystals around it, they started exploding and doing all their things. But the spinel crystal was kind of looked completely unaltered up to 900, even 1100 Celsius. So we checked in the Raman signal if we saw the same thing. And here we do see a dramatic change once we go up to that 750 Celsius. Because we know that gem spinel, the structure changes a little bit once we cross, I believe it is around 650. And there we get a broadening of that main peak around 420, and it shifts a little bit as well. And that's a criterion we use for spinel heat treatment detection. But we see the exact same thing happening in spinel inclusions in rubies as well, where we see that in the unheated state and at 600 Celsius, these spinels are completely intact. The crystal structure hasn't changed. But once we cross over to 750, we see in the Raman signal that something has changed in that spinel. It has been subjected to higher heat. Now remember, visually, these things look all exactly the same. So this is a case where advanced technology gives us more information than we can get with the microscope. Another technique that we looked at is Billie's specialty, so she's going to talk about that one.
Yeah, and this is really going back to, a little bit more advice when you're working in the lab. We really don't rely on just one test. There's no one instrument that we can put the stone in that'll spit out an answer for us. But we really put every stone that comes into the lab through a series of different tests, and we look at the evidence from all of them combined before we draw a conclusion. And that's what we're trying to do here. So we've looked a little bit at the inclusions, we looked at the Raman spectroscopy, and we're also going to look at the UV fluorescence. Now we looked at all the stones both in long wave and short wave. This is what one of our samples looked like in long wave, unheated. And I would say that across all the stones we heated 15 samples, the fluorescence reactions from stone to stone were fairly consistent. They all looked very similar before and after. So before the treatment, we saw this really strong red fluorescence in the long wave. And after heat treatment, it was still a very strong red. So it didn't change much in the long wave. And we did look at it between each stage of heating, but it looked fairly consistent from stage to stage. Now you might notice that on the right side of the stone you see kind of a band of stronger red color. That's not a change in the fluorescence, it's because the stone has developed a fissure in that area after the heat treatment, and so the light is just bouncing off the fissure. But it's not a real change in the fluorescence of the body of the stone. And this was pretty consistent stone to stone. We also looked in the short wave, of course. This is what one of our samples, the same sample actually, looked like when it was unheated. And you can see that the fluorescence is a little bit more of a pinkish red color, but it's still a very strong red reaction. During our lower temperature stages, we didn't notice any significant changes in the fluorescence, but we did notice when we got to 1500 degrees. The stone became a little bit more pinkish, and it started to develop a chalky appearance, which is a more whitish appearance. Here's another one of our samples, unheated, and you can see that the stone, I don't know if you can see it on the screen very well, but the stone is a little bit milky in one area. After heat treatment, we could see that very clearly, where that cloud of silk became very strongly chalky. And so this is associated with the areas where the rutile silk is starting to dissolve. Here's another one of our samples when it was unheated. Again, red fluorescence, quite strong, and it does develop a more chalky appearance after the heat treatment. Now in this sample, you'll also see that there's some kind of round, very bright droplet-looking areas. This is not something that's going on inside the stone, but this is material that's fusing to the surface of the stone. So sometimes when you heat material, you will get these kind of frozen droplet-like areas on the surfaces. And normally an experienced treater will repolish the stone after this kind of treatment to remove these droplets.
So yeah, I think there's a couple of points that we want to summarize about this whole talk. And one of the first things is that low temperature heat treatment has an incredible relevance in today's market. Now that doesn't mean it's a new thing. You can look at manuscripts that are over 800 years old, and they describe exactly the same way that Sri Lankan gentleman that we saw in the first slide is doing that. So that's been going on for hundreds of years. It is just becoming more challenging to detect right now, so it is a really big issue for laboratories. So that's why we focus on this project, because the detection and even the awareness about this treatment is very limited within the gemological community. And while laboratories, we've been studying this for nearly a decade, a lot of people are still unaware about this treatment, the impact that it has, and the impact that it has on the classic criteria that we use for heat treatment detection. So the clues that can help, basically when we look at inclusions are still one of the most valuable techniques. Even working at major labs like GA and Lotus, the first thing that happens to a stone is not pop it into $1 million machine. The first thing that happens is we look at the inclusions, we look at it in the microscope. The microscope is and probably always will be the workhorse of the gemological laboratory. All the other things are supplements, but the information we can get from the study of inclusions, the observations of the internal world of the stone, are invaluable. Another thing that we can't ignore that advanced instruments are making their way into the lab for sure, but also into the everyday gemological community. I think all of you that work with diamonds mostly have diamond screening instruments with advanced instrumentology in it in your office. Colored stones can't lag behind. So there is a lot of value in supplementing your information with advanced instrumentology, like the spinel crystals that we looked at during heat treatment. Visually, in the microscope, they didn't show any changes. But with the advanced techniques, with Raman spectroscopy, we could see that these were actually heated. And then that fluorescence is an underrated tool for treatment detection. And actually with a lot of things. But it is a very dangerous tool. It is very difficult to interpret. It is very difficult to judge. Because especially right now we see different models of UV lights coming in. And it is again there. Compare apples to apples. I see a lot of people run around with these new long wave LED torches. I think you can buy these for like $60. They will make everything glow like the craziest fluorescence. Don't judge your fluorescence using these tools. Make sure you are always looking in the standardized environments, that you keep comparing apples to apples. The same thing goes with shortwave fluorescence. There are instruments out there that bring extreme deep UV fluorescence with an extreme intensity that is going to mislead you very often if you don't internally calibrate for that. Because every stone is going to show chalky fluorescence if you put it in a diamond view, which is an extremely deep UV with extreme strength. So make sure that you look at all these things under the same conditions, and only then is when you will start noticing all these patterns.
I think that's a good point you make about the fluorescence. And I was approached by someone who was working for a major retail jeweler, and they were asking me about this. And they said, we're looking at different rubies, Burmese, Mozambique. And I was wondering, do those Mozambique rubies, do they fluoresce? And what I was saying is, how we describe it in the lab is we don't look at it as a yes or a no. We don't describe it in our database as like, yes, it fluoresces, no, it doesn't fluoresce. We say, what color is it fluorescing? And we try to give it an idea of the strength. Is it fluorescing strongly or weakly? Is there a chalky zone, or is there different colors? Sometimes we see a little red and a little bit of orange, for example. And so I agree, you have to be a little bit more careful in the way that we're looking at this and describing these things that we're seeing.
Yeah, and I think the most important thing if you do these descriptions is that you calibrate them all to the same standard, because obviously if you have a 30-year-old UV box with one of those fluorescent tubes in it, and you compare it to shining this LED torch in its face, obviously it's going to give different results. It's going to be a lot stronger. So it's important that you calibrate all your observations when it comes to those fluorescence observations.
And when you're looking in a UV box, those standard UV boxes that a lot of labs have, even consider how close you hold the stone to the light will affect how strong you're seeing a reaction.
Absolutely. So if you are interested in this topic, and I think the fact that you're all here means that you are interested, there is a lot of information out there available for free that you can read up, that you can study further. So Billie has done a big project on Madagascar sapphires, because now we only focus on Burmese rubies. We have done a lot of work, Billie's done a lot of work on Madagascar sapphires, the blues mostly, and I think recently more of the work on pink material has been done. You can find this in the Gems and Gemology issues from summer 2019, which you can also buy at the GIA booth. I think they are selling those for around $10 a piece, those older issues. We did publish an article about this whole project on Burmese rubies, also in Gems and Gemology, which you can read online for free and also get at the booth. But
we have one more thing prepared for you before we run out of time today. People who know me know that I love trivia games, so I thought we would play a little game here today. And like any good game, there is a prize if you win, which we've furnished. We have copies of G&G for the winners. And so we kind of wanted to see how closely you guys have been paying attention. So let's get started. We're going to look at this, and these are also in Burmese rubies. I'll give you that little hint. And we wanted to see if anybody could guess the crystal. So I think over here you were the first to raise your hand. Okay, so the guess was calcite, which is a very good guess because calcite was one of the crystals that we saw the most commonly in this material. But unfortunately, in this case, it was not the correct answer. So maybe somebody else wants to. Art, how about you? Spinel, very good. It is indeed spinel. Do you want to tell us why you thought it was spinel? Exactly. You notice that there's kind of an octahedral shape to some of these crystals. So again, there are some clues there, even if you don't have access to a microromon. Yeah. And you can come up to us after we finish up here to get your prize. Let's try another one. Here's another crystal. Anybody want to guess? Okay, let's have it again. Oh, man. It's still a good guess because it's very common, but it's still not quite there. How about in the back? Very good. It was indeed mica. And you'll notice that there's a real texture here, and you see a lot of striations across the crystal. So this is a mica crystal.
I think the two giveaways for this to be mica is, because it doesn't really look like a mica crystal, but it's the coloration that's like a little tint of like almost brownish in it. That is pretty unusual for Burmese ruby crystal, Burmese rubies inclusions. But the most important is like that parting, that breaking up of that crystal. And these are all the thin mica layers that we see stacked on top of each other. So yeah, this is a mica crystal.
And we have one more chance for one last winner. Adrian? Very good.
Third time's the charm.
I'm sorry. So thank you guys for all of your wonderful guesses. These are indeed calcite, the most common crystal that we found. And thank you all for coming out here today.
Thank you.